Today, we are going to explore how we can terraform our neighboring planet, Mars. Terraforming means making a planet suitable for terrestrial life. Each planet is very different from the others, so each requires a unique set of steps for terraforming. Let's examine what those steps are for Mars. Mars is the fourth planet from the Sun in our solar system and is located approximately 1.5 astronomical units from the Sun, which means it is 1.5 times the average distance between Earth and the Sun. Commonly referred to as the red planet due to the large amount of iron oxide on its surface, Mars is one of the four rocky planets in our solar system and the most similar to Earth. Although its average temperature is about minus 63 degrees Celsius and its atmospheric pressure is only 0.6% of Earth's. But let's get to the point. What do we need to do to terraform Mars? We could start, for example, with water. This indispensable substance for life is much more abundant on the planet than most people think. In fact, there is so much water just at the south pole of the planet that if it melted, it could cover the entire surface of Mars under 11 meters of water. The problem is that this water is mostly in the form of ice. For the planet to be habitable, it would be logical for this water to be in a liquid state. So, what needs to be done for that to happen? For that, we need to delve into thermodynamics. Let me introduce you to the phase diagram of water. This diagram shows the relationship between pressure, temperature, and the states of matter. Normally, we all know that water boils at 100 degrees Celsius and freezes at 0, but the key here is the normally part because these temperatures are at the pressure of 1 atmosphere, which is the atmospheric pressure at sea level on Earth. This diagram predicts, for example, why water boils at about 70 degrees Celsius on Everest, or how pressure cookers work by increasing the pressure so that liquid water can reach higher temperatures, specifically up to about 130 degrees Celsius, which allows food to cook faster, reducing cooking times by about 4 times. The same concept of a pressure cooker can be applied to Mars. If we plot a point on the diagram with the pressure and temperature conditions found on the surface of the red planet, the point falls just below the minimum pressure at which liquid water can exist, no matter how much heat is applied. This is why the water on Mars is either solid or vapor. The solution to this problem is right in front of us. We just need to modify the parameters so that the point falls within the liquid water zone, which translates to increasing the pressure and temperature. But how do you increase the water, pressure, and temperature? There are many ways to do this, but one of the most interesting options is one that allows all three to be achieved simultaneously, bombarding the poles. Besides containing water, the poles contain carbon dioxide. If the carbon dioxide at the poles in the form of dry ice were heated just a few degrees, it would sublimate, triggering the following events. First, atmospheric pressure would increase to 0.3 atmospheres, which is 0.3 times the atmospheric pressure at sea level on Earth and the same pressure as at the summit of Everest, allowing people not to need space suits. Then, a potent greenhouse effect would start to occur as more and more CO2 would increase the temperature, melting the poles further, thus initiating a positive feedback loop. This process could be initiated in various ways, such as bombing the poles with hydrogen bombs or using orbital mirrors to melt the poles. If we opt for bombing the poles, just the nuclear arsenal of the USA and Russia would suffice. At this point, we would already have a planet with liquid water and a significant atmosphere. However, this atmosphere would be mainly composed of carbon dioxide and water vapor, leading to another problem, the lack of oxygen. This problem, fortunately, can be easily solved with the help of phytoplankton, the source of half the oxygen on Earth. These organisms can convert carbon dioxide into oxygen, making them ideal as the first colonizers, gradually making the Martian atmosphere more like Earth's. A faster method could also be used, electrolysis, which is the artificial production of oxygen from water. Here, we need to make a parenthesis because there are a couple of important nuances to mention, one good and one bad. The good news is that to heat the atmosphere, fluorine compounds could be used, which are about 1,000 times more efficient than CO2 as planetary warmers, accelerating the process. The bad news is that even if we release all the CO2 present at the poles, the atmospheric pressure would still be insufficient. As mentioned, it would be the same as on Everest, where there is no life. Despite this, we would be close to achieving a suitable pressure, which could be achieved in two ways: bringing gases from other celestial bodies such as comets or moons like Titan, the more viable option, or generating them from the planet's rocks, which could release large amounts of gases through simple chemical processes. It's important to highlight that we don't know what's beneath the planet's surface, as we've only dug a few centimeters deep. There could be enormous reservoirs of water and carbon dioxide sufficient to create an atmosphere with adequate pressure. As you can see, terraforming Mars is not as difficult as it seems. As SpaceX founder Elon Musk said, it would suffice to bomb the poles with a few hydrogen bombs which are not radioactive and fill the atmosphere with a bit more gases. We might need a bit more temperature, but we have unfortunately demonstrated our capability to heat planets. At this point, we would have a planet suitable for life, except for one small problem. Actually the biggest one, the lack of a magnetic field. The greatest challenge to human space colonization is not temperature, water, or energy, but radiation. High-energy particles in space make it an extremely inhospitable environment for life. If a planet lacks a magnetic field, these particles, also known as solar wind, can quickly strip away any atmosphere the planet might have, which is what happened to Mars in the past. It once had a dense atmosphere that it lost when its powerful magnetic field disappeared about 4 billion years ago. Thus, creating a magnetic field is essential to protect both living beings from radiation and the atmosphere from being eroded. However, creating a magnetic field is complex. Mars lost its magnetic field because its core, which generated it, cooled down. On Earth, the outer core remains liquid, providing us with a strong magnetic field that protects us and our atmosphere from the solar wind. We need to warm Mars' core to reactivate its magnetic field. While this would be a good option, it would require thousands of billions of bombs like the Tsar Bomba, the most powerful bomb ever detonated by humans, and first, we would have to transport these bombs to the core, which is currently impossible due to the extreme pressures and temperatures that would make it impossible to reach such depths. Fortunately, there are more viable options. We can create a magnetic field ourselves. A study conducted in 2008 by the Japanese National Institute, motivated by the potential absence of a magnetic field like what we might face on Earth in a few decades due to natural weakening, calculated that we could generate an artificial magnetic field strong enough to protect us from the solar wind by constructing 12 parallel cables around the Earth's equator, each with a diameter of only 60 centimeters, made of superconductors, consuming the feasible power of 1 gigawatt with a current of 6.4 megaamperes. Obviously, constructing 12 superconducting cables around the world is not cheap or quick. But once the Martian atmosphere is created, it would take several centuries for it to disappear, giving us plenty of time to extract materials from Mars. And don't forget that Mars is much smaller than Earth, so fewer resources and less time would be needed to build the necessary cables to create an artificial magnetosphere. If we overcome this last step, we would have a terraformed Mars. What is currently a hostile, cold, and desert-like world would become a welcoming planet, a true sibling to Earth. We would have a second blue marble in this solar system, ready to be filled with life. This second home would greatly reduce our risk of extinction and kickstart the human expansion into space. The best part is that we can do it. We need to overcome certain technological and scientific obstacles, but it is feasible. It is just a matter of will, not the will of a few, but the will of all humanity, of our entire species, which I believe has the mission to spread life throughout the universe to save it.